Welcome to the debate. Today, we're diving deep into one of cosmology's most enduring mysteries, the fundamental forces that sculpt the universe's grandest structures and will dictate the intricate dance within galaxies. Our central question today emerges directly from the, I think, groundbreaking work of author Jay Alfred. Does his dark plasma universe hypothesis, this framework where dark matter exists in a dynamic, electrically charged plasma state, does it offer a more comprehensive and frankly robust explanation for cosmic structure formation and galactic dynamics, things like galaxy rotation and those enigmatic galactic shells? Does it explain these better than models that rely solely on the gravitational interactions of largely, inert dark matter? I'll be arguing that J. Alfred's framework provides a really powerful and unified explanation for these cosmic puzzles, seeing dark matter as an active, dynamic force.
And I'll be critically scrutinizing the unique contributions and implications of this dark plasma hypothesis. I want to explore where it truly enhances our understanding, or perhaps where it might unnecessarily complicate things. My core focus really is whether this new physics offers unique, testable predictions that simpler, gravitationally focused models cannot. Does it truly push our understanding forward in a fundamentally new way?
Right. J. Alfred's dark plasma universe isn't just, another model. It's presented as a truly holistic explanation that reimagines dark matter entirely. He posits what he calls a ghost universe of dark plasma. Essentially, this means dark matter existing not as these inert cold particles we often talk about, but in an ionized, electrically charged state, capable of conducting currents and interacting electromagnetically, albeit perhaps weakly, alongside its gravitational influence. Alfred proposes this dark plasma acts as a kind of dynamic template, influencing cosmic structure formation through its inherent density, temperature, viscosity, and of course, gravitational forces. A crucial insight here, I think, is that this active dark plasma, particularly as a significant component of cosmic filaments, those vast thread-like structures spanning the universe, is what drives the coherent rotation of these filaments and subsequently the ordinary matter within them.
Okay. I understand the appeal of a unified framework. I really do. But my immediate question is about its fundamental necessity. The premise that dark matter is in a plasma state with some weaker charge and sustained charge separation, well, that introduces a significant layer of new physics. Physics we haven't directly observed in the dark sector. The role of these proposed hidden dynamics, even if they're transmitted mainly through gravitational interactions, needs careful justification. Do the observed cosmic phenomena we're discussing today require these specific, quite complex dark plasma dynamics? Or can conventional gravitational dark matter models, maybe with some additional refinements, still adequately explain them? I mean, for instance, we've seen fascinating dusty plasma experiments in labs showing self-organization in voids that, yes, resemble the cosmic web. But extrapolating those microscopic lab conditions to the sheer vastness of cosmological scales.
That demands extremely robust evidence and, crucially, some distinct predictions.
And that's precisely where Alfred's model shines, in my view. It offers a specific mechanistic explanation rather than requiring constant sort of refinements to existing models that don't quite fit. Let's delve into our first core point of debate, the primary drivers of the cosmic web and galaxy rotation. Alfred's work explicitly attributes the coherent rotation observed in cosmic web filament and, consequently, within galaxies themselves, to the underlying dynamics of this dark plasma. He details how, within these filaments, specific, weak, long-lived dark currents form what he calls helical dark Birkeland currents. You can think of these as cosmic electric filaments, almost like vast, twisting ropes of dark plasma carrying electric current across immense distances.
Right, I appreciate the visual of these cosmic electric filaments, but how exactly do they translate to the visible galactic rotation we see? And what makes this mechanism so uniquely necessary compared to other ideas?
That's an excellent question. Alfred explains that these dark Birkeland currents, through a process called the pinch effect, where the magnetic fields generated by the current actually squeeze the plasma inwards. They compress the dark plasma to form dense structures. He calls them plasmoids. These plasmoids, he suggests, are essentially embryonic galactic structures. Furthermore, the Hall effect, which is an interaction between the plasma current and a magnetic field, imparts a specific spin. It basically converts directional electromagnetic tension into rotational coherence for these emerging structures. It's a fundamental plasma mechanism we understand well. These rotating dark Birkeland currents then gravitationally tug on ordinary matter, inducing the rotation we observe. So this provides a plasma-driven cause for rotation that also coherently aligns galactic spin axes with the cosmic filaments, a phenomenon that's actually been observed in large-scale structure surveys. It's not just a generic tug, it's a structured, plasma-driven spin.
That's a very detailed mechanism, I grant you, and I can see the elegance in proposing a single unified driver. However, that phrase, additional cause, well, it raises a red flag for me. It sort of implies that other established causes are somehow insufficient. Current simulations and observations already confirm that cosmic filaments rotate. But is this full suite of dark plasma dynamics the specific instabilities Alfred describes? The sustained charge separation, the helical magnetic fields, these weak charges, is all of that strictly necessary to explain this rotation? Or could other factors, like, say, the initial angular momentum reservoirs present in these absolutely massive structures, plus conventional gravitational interactions, could those contribute significantly? We already model these filaments as anisotropic structures possessing immense angular momentum. Could refining our understanding of those gravitational dynamics and initial conditions explain the observed rotation and alignment without needing to introduce an entirely new dark plasma physics? What's the definitive observational signature of these dark Birkeland currents that would differentiate them from conventional angular momentum transfer?
But those refinements, to my mind, often feel like, well, ad hoc additions, almost like patching over missing physics. Alfred's model offers a foundational, unifying mechanism for phenomena that existing models frankly struggle with. For example, this same inherent self-organizing property of dark plasma offers a remarkably elegant solution to another long-standing enigma, the flat galaxy rotation curves. For decades, observations have shown that stars and galaxies rotate at nearly uniform speeds, even far out from the galactic center, completely defying predictions based solely on visible matter. Alfred posits that the self-interacting dark plasma isn't just some diffuse cloud. It actively organizes itself into nested, prolate elliptical shells, essentially. Think elongated, football-shaped layers surrounding the baryonic disk.
Nested shells of dark plasma? How would that lead to flat rotation curves in a way that's distinctly better than our current dark matter halo models, which already do a pretty good job?
Well, the key is in the dynamics of the plasma itself. Alfred argues that this dark plasma, through its electromagnetic tension and pressure, maintains a coherent mass-energy density across vast radii. Imagine the dark matter halo not just as a static distribution of particles, but as a series of concentric, interconnected, electromagnetically structured shells. This self-organization, driven by its plasma state, then acts as a gravitational template, effectively molding the baryonic matter within it. The result? Stars rotate at nearly uniform speeds, producing the flat rotation curves we observe. It's analogous, he argues, to how magnetized plasma filaments behave in laboratory settings, where the internal structure maintains a stable configuration. It's not just about having distributed mass. It's a dynamically self-organizing system that actively shapes the gravitational potential.
I have to say, I'm not entirely convinced by that line of reasoning. The existence of dark matter halos, even without invoking explicit plasma dynamics, is already, very effectively used to explain flat rotation curves, while Alfred posits a rotating dark Birkeland current and these specific shells. The core question for me remains, what critical distinction makes the dark plasma explanation genuinely superior to a generalized, distributed dark matter halo? A halo that, gravitationally speaking, is already providing a pretty good fit to the data. If the electromagnetic effects of these currents aren't directly felt by ordinary matter, only their gravitational influence, then how does this coherent electromagnetic structuring provide a distinctly better fit or maybe more predictive power than other dark matter models? Many existing models can already achieve the desired mass distribution without adding the complexity of a plasma state. Does Alfred's model predict, say, subtle deviations in rotation curves that standard models miss, or perhaps a specific anisotropy that could actually be measured?
The distinction, in my view, lies fundamentally in the mechanism of that distribution and its self-organization. It's not just that the mass is distributed in a certain way, but how it gets there and why it maintains that specific form. This dynamic self-organization is a really powerful aspect. Finally, let's pivot to another fascinating puzzle: the formation of concentric shells in elliptical galaxies. We observe these incredibly delicate, almost perfectly symmetric shells in ellipticals like NGC 7600 and NGC 3923. They extend way out, sometimes 2 to 3 times farther than the bulk of the starlight, and some galaxies have like 20 or more shells. The standard explanation involves galactic mergers.
Yes, and the merger model has considerable observational and simulated support, it's fair to say.
Exactly. But Alfred offers a powerful alternative that I think accounts for their striking symmetry and persistence without needing recent, potentially chaotic mergers. He proposes that a self-interacting dark plasma component within the dark matter halo actually forms stable, nested concentric shells through inherent plasma instabilities. Things like double layers, which are regions of charge separation that act like capacitors in plasma, and standing wave patterns. These are all well-understood plasma phenomena. These stable dark shells then act as gravitational templates, molding the ordinary baryonic matter into the visible shells we observe. As Alfred noted back in 2005, he said the presence of shells in dark matter around galaxies suggests its plasma state, implying a fundamentally different formation process. It's a beautiful, self-organizing explanation for these highly ordered structures, isn't it?
I see why that's an intriguing point, yes. And the elegance of a non-merger explanation is certainly appealing. However, the merger model for shell galaxies is quite robust. It attributes these shells to processes like phase wrapping, essentially, where stars from a disrupted galaxy fall into the primary galaxy's potential and orbit, creating these ripples that appear as shells, and just general tidal debris from galactic interactions. So the question becomes, what specific characteristics of these shells, maybe their number, their precise spacing, or perhaps even their chemical composition, does Alfred's dark plasma model predict that are not explained by these well-supported merger scenarios? Or does it merely offer a different pathway to a similar outcome without providing truly distinctive, testable signatures? The idea of dark matter just self-organizing into these precise structures, well, that's a significant conceptual shift. It needs strong, distinctive corroboration beyond just the aesthetic appeal of the explanation. How would we even observationally distinguish a dark plasma shell template from a tidal debris shell?
Well, I'd argue the sheer number and the striking symmetry of these shells, especially extending so far out, can be quite challenging for the merger model to consistently produce without requiring multiple, very precise merger events. Alfred's model, by contrast, suggests an intrinsic, self-organizing property of the dark matter itself. It's potentially a stable, persistent template. Perhaps the predicted long-term stability and the precise spacing, which might follow from plasma wave mechanics, could offer that distinctive signature we're looking for.
That's a fair point regarding the challenges of multiplicity and precision in merger events. Yet, our simulations of mergers are constantly improving, and they can reproduce many of these features quite well now. For Alfred's model to truly displace the merger hypothesis, it would need to make unique predictions that are currently unexplained by mergers, or perhaps actively contradict them. Without that specific testable prediction, it remains, for me, an elegant but ultimately unproven alternative, an additional layer of complexity that hasn't yet demonstrated its empirical necessity.
And I would argue that its unifying power across multiple disparate cosmic phenomena is its strength, suggesting perhaps a deeper, underlying physical reality we haven't fully grasped.
A truly unifying power would be evident in those unique predictions and distinct observational tests. That's really what we need to pursue, I think.
Absolutely. Testability is paramount, I agree. Today, we've explored Jay Alfred's compelling hypothesis of a dark plasma universe, presenting it as potentially an active template for cosmic structures. This framework suggests that the plasma state of dark matter, with its unique electromagnetic dynamics, might offer a unified explanation for the coherent rotation of cosmic filaments and galaxies, the flattening of galactic rotation curves, and maybe even the formation of enigmatic galactic shells, moving beyond purely gravitational interactions to a more active, plasma-driven cosmic architecture.
And we've critically examined the compelling aspects, but also the challenges of Alfred's dark plasma hypothesis. It certainly presents an intriguing alternative, suggesting that plasma dynamics might play a far more active role in the universe's large-scale structure than traditionally assumed. However, the real rigor lies in discerning precisely where this model offers genuinely novel and testable predictions that are distinct from existing astrophysical explanations, which, let's remember, rely heavily on gravitational dark matter models and well-understood baryonic physics. Our discussion today, I hope, underscores that the universe's immense complexity often demands multiple perspectives for true appreciation, reminding us that there is always more to explore in the material. The debate certainly remains open, inviting all of you listening to consider the implications of a potentially dynamic dark plasma in shaping the cosmos.